Right now, at this exact second, the very act of you listening to this conversation is physically altering the structure of your brain.
Yeah, I mean, it sounds like a philosophical metaphor or something, but it's a literal biological reality.
Right, because every acoustic wave carrying our voices is vibrating against your eardrums and then being translated into a cascade of electrical impulses. And those impulses are like currently rushing through your neural networks, sculpting new microscopic connections inside your head.
Exactly. You will not have the exact same brain at the end of this deep dive as you do right now. What we're talking about here is the mechanism of neuroplasticity.
Which is just wild to think about in real time.
It really is. So when you encounter new information, your neurons fire in novel patterns. We have this fundamental rule in neuroscience called Hebbian theory, which states, neurons that fire together, wire together.
Neurons that fire together, wire together.
Right. Yeah. As you focus on the concepts we're about to discuss, the synapses connecting your neurons are actually releasing neurotransmitters. And if that firing is sustained and repetitive, the physical architecture of those synapses will thicken.
So they literally get beefier.
They do. They become more efficient. You are currently building a new neural architecture just by paying attention to my voice.
That real-time biological remodeling sets up our entire mission for today's deep dive. We're going straight into the core insights of Norman Doidge's landmark work, The Brain That Changes Itself.
Such an incredible piece of source material.
Oh, absolutely. And the goal here is to completely dismantle a medical dogma that was culturally and scientifically entrenched for like over 400 years. We're going to break down the old, stubborn idea that the adult brain is a static, hardwired machine.
Right, the old view was so limiting.
It really was. We want to replace it with the cutting-edge reality of a brain that could physically rewire itself to overcome catastrophic damage, reverse paralysis, and even cure learning disabilities.
To really understand the magnitude of this shift, we have to look at the neurological consensus of the 19th and 20th centuries. The overarching theory back then was called localizationism.
Localizationism, which basically meant every part of the brain had one specific job, right?
Exactly. Scientists mapped the brain and discovered that specific areas seemed strictly dedicated to specific functions. There was a visual center, a language center, a motor center.
Like a factory where every machine only does one thing.
That's the perfect analogy. The logical, albeit totally flawed, conclusion they drew was that the brain was like a manufactured machine with fixed circuits. So if a stroke or trauma destroyed the language center, the ability to speak was just gone forever.
Wow.
Yeah, they believed you couldn't grow new neurons, and you certainly couldn't rewire a visual center to handle language. The biological destiny of an adult brain was essentially fixed.
So if the machine broke, you just had to, learn to live with a broken machine. That must have been a profoundly bleak prognosis for millions of people.
It was devastating.
Okay, let's unpack this. Because the evidence that shattered this localization dogma is astonishing. And it starts with a woman named Cheryl Schultz. Her case study doesn't just challenge the idea of a fixed brain. It completely redefines our understanding of human senses.
Cheryl's reality was, quite frankly, a waking nightmare. Following a routine post-operative infection, she was prescribed an antibiotic called gentamicin.
Just a standard antibiotic.
Yeah. But in rare cases, gentamicin toxicity can completely destroy the vestibular apparatus. Those are the delicate structures inside the inner ear that govern our sense of balance.
The inner ear. Right.
For Cheryl, the medication eradicated the hair cells in her semicircular canals. These are the microscopic sensors that detect the movement of fluid in your ear and, tell your brain where your head is in space.
Which is something we totally take for granted. You're sitting down right now. You inherently know you're sitting. You know which way the floor is.
Exactly. Your brain is constantly running that background calculation.
But for Cheryl, that baseline data stream was suddenly just gone. And the silence from her inner ear caused her brain to panic, right? It interpreted the lack of signal as catastrophic, continuous movement.
Yes. To her, the world felt like it was constantly collapsing.
I can't even imagine. Even when lying flat on the floor, she felt like she was endlessly plummeting off the edge of a sheer cliff. She was paralyzed by this primal fear of falling and just debilitating nausea.
And traditional neurology offered her zero recourse. Because of that localization dogma we mentioned, doctors understood the inner ear as the sole hardware for balance.
So if it's broken, it's broken.
Exactly. If the hardware was permanently destroyed by toxicity, the function was permanently lost. They essentially told her she would be a wobbler for the rest of her life, unable to stand or walk without leaning on walls.
But then a pioneering neuroscientist named Paul Bach-y-Rita entered the picture. And he just flat out rejected the localization premise. He didn't look at Cheryl and try to invent, like, a surgical fix for her inner ear.
Right, he assumed the inner ear was a totally lost cause.
Instead, he made this staggering leap in logic. He aimed to bypass the ear entirely and feed the balance data to her brain through her tongue.
Wait, through her tongue? I know, it sounds bizarre, but Bach-y-Rita understood that the brain is essentially a dark box. It has no idea what an ear or an eye actually is.
It's just sitting in the dark skull waiting for signals.
Precisely. It only understands electrical impulses. So he designed an external sensory substitution device. It started with this construction-style helmet fitted with a physical accelerometer.
Like the exact same technology inside your smartphone that knows when you turn the screen sideways.
Yeah, the exact same concept. So the helmet is doing the mechanical job of the inner ear, measuring the tilt and pitch of her head.
Got it.
And then that accelerometer was tethered to a computer, which translated that spatial data into electrical pulses. Those pulses were then sent to a small strip, essentially a grid of electrodes, that Cheryl placed directly on her tongue.
If we break down the mechanics of this, it is brilliant because the tongue is packed with tactile receptors. And it has a massive representation in the somatosensory cortex, which is the brain map that processes touch.
Oh, it is prime neural real estate. When Cheryl tilted her head forward, the accelerometer detected it, and the computer sent a buzzing sensation to the front of her tongue.
Okay, so she feels it in the front.
Right, and if she leaned back, the buzzing moved to the back of her tongue. If she tilted left, it buzzed on the left. Bach-y-Rita was giving her brain a stream of artificial spatial cues encoded in tactile vibrations.
So it's basically like a major highway bridge collapsing the inner ear.
Mm-hmm.
And the brain suddenly learning to detour all the traffic through a winding back road, which is the tongue, just to get to the same destination.
That is a brilliant way to put it. Initially, it just felt like weird buzzing to her. But after a few minutes of wearing this device, Cheryl's brain began to decode the pattern.
It figured out the back road.
Yeah. It realized that the buzzing on the tongue correlated with the physical movement of her body. And here is where the absolute magic of neuroplasticity kicks in. Her brain took that tactile data from her tongue and actively routed it away from the touch centers.
Wait, really? It rerouted it?
Yes. It sent it directly into the vestibular nucleus, the balance center of the brain, and she stood up without falling.
That gives me chills.
The brain bypassed the broken neural highway of the vestibulocochlear nerve and forged a completely new detour using the cranial nerves of the tongue. It allowed her to stand, close her eyes, and maintain perfect equilibrium.
But the most profound discovery wasn't just that the helmet worked while it was on her head. It was what happened when she took the helmet off.
The residual effect.
Right. After a 20-minute session, she would take the electrode off her tongue, and she didn't instantly fall over. Her balance remained stable for minutes, and eventually, after weeks of training, for hours and even days.
And this is where we see the physical architecture of the brain actually changing. The temporary electrical detour forged by the device triggered synaptogenesis.
Which is the creation of new synapses.
Exactly. By constantly forcing the brain to route spatial data through the tongue, her neurons began to physically strengthen those specific pathways. Even more fascinating, scientists suspect her brain began to unmask and strengthen latent, dormant pathways that already existed but were previously, too weak to be useful.
Her brain permanently rewired its own hardware to stabilize her sense of gravity. That is just incredible.
It is. If the brain can reassign the tongue to do the job of the inner ear, that completely shatters the localization dogma. It implies the brain doesn't actually care where the sensory data originates.
All right, the visual cortex, the auditory cortex, these aren't strictly hardwired to our eyes and ears. They are just incredibly efficient data processors waiting for a signal.
And that realization led Bach-y-Rita to question the very nature of human perception. He pushed the boundaries further and raised a paradigm-shifting question. Do we actually see with our eyes, or do we see with our brain?
Because when you really look at the anatomy of the eye, it's just a biological camera lens. The eye itself doesn't possess consciousness.
No, not at all.
The retina just captures photons of light, converts them into electrical spikes, and fires them down the optic nerve.
The optic nerve is just a bundle of cables carrying a chaotic storm of electricity. There are no actual images traveling through your brain.
It's just code.
Right, it's just raw code. It is the primary visual cortex located at the very back of the skull that receives this raw electrical code and learns to interpret it as shapes, colors, and depth. The visual cortex is what actually sees.
So Bach-y-Rita reasoned that if a person is blind due to retinal damage or cataracts, their visual cortex might still be perfectly intact, right? It's just sitting in the dark, starved of electrical impulse.
Exactly, waiting for data.
So if you could somehow feed raw, structured spatial data to that visual cortex, the person should, theoretically, be able to see again.
And that led to his next invention. He developed the tactile vision substitution system. He mounted a low-resolution video camera on a pair of glasses.
Okay, so the camera is the eye now.
Yes. The live feed from the camera was routed to a computer, which translated the bright and dark pixels into a grid of physical stimulators. He placed this grid against a blind person's skin, initially on their back, and later on the tongue.
So the brighter the pixel on the camera, the stronger the vibration on the skin. And a dark pixel meant no vibration at all.
Right. So if a researcher held up a bright white ball in front of a dark background, the blind patient would feel a circular pattern of buzzing on their tongue or their back.
Okay, I have to play devil's advocate here, because if you put a vibrating grid on my back and it buzzes in the shape of a circle, I am going to feel a circle on my skin. I can cognitively deduce, like, oh, you are holding a ball. But I wouldn't call that seeing. That is just complex touch. How do we actually cross the threshold from feeling vibration to perceiving vision?
That is the most critical distinction in this entire field. In the very beginning, the blind subjects experienced exactly what you described. It felt entirely tactile.
They just felt buzzes.
Right. They had to use immense cognitive effort to deduce the shapes based on the buzzing. But as they practiced navigating the world with the camera, a massive neurological shift occurred. Cross-modal plasticity took over.
The brain started routing the tactile data away from the somatosensory cortex and plunging it directly into the visual cortex.
Yes, brain scans confirmed it. The primary visual cortex of these blind patients lit up in response to the tactile stimulation. Because the visual cortex is structurally evolved to process things in terms of depth, parallax, and spatial relationships, it naturally applied its visual algorithms to the tactile data. The subjective experience of the patients fundamentally altered.
So they stopped feeling the buzzing on their skin.
Exactly. The feeling on the skin faded away, and they began to perceive objects out in the three-dimensional space in front of them.
The skin effectively became a retina. The sensory input lost its tactile quality and took on the subjective quality of vision.
They could perceive perspective. If an object moved closer to the camera, the buzzing pattern grew larger. But the visual cortex decoded that expansion as approaching, not just more buzzing.
That is mind-blowing.
They could identify faces, read signs, and famously, they could bat a rolling ball as it moved across a table.
Catching a moving object requires real-time, subconscious spatial calculation. You cannot do that through conscious deductive reasoning.
You really can't. The visual cortex had successfully hijacked the tactile signal. The sensory regions of the brain are clearly not rigidly fixed to specific organs.
We've established that the brain can reroute sensory input. But what happens when the damage isn't sensory, but motor? What happens when a brain injury paralyzes the physical body? Like, specifically in the context of a stroke.
Stroke recovery represents one of the darkest chapters in medical history, primarily because the localization dogma actively condemned millions of people to permanent disability.
The medical consensus for most of the 20th century was exceptionally grim. If you suffered a stroke, say a blood clot deprived a section of your motor cortex of oxygen, and that brain tissue died, you would likely lose the ability to move an arm or a leg.
And the prevailing wisdom dictated that whatever spontaneous physical recovery you made within the first 6 months was your absolute ceiling.
After 6 months, the brain was considered settled. The damage was permanent.
But the tragedy is that this 6-month window was a self-fulfilling prophecy, born out of a complete misunderstanding of how brain maps work. It wasn't until a neuroscientist named Edward Taub challenged the dogma that we understood the real mechanism keeping these patients paralyzed. Taub was conducting research on deferentation.
Which is cutting the sensory nerves in monkeys, right?
Yes. Taub surgically severed the sensory nerves going to one of a monkey's arms. The monkey couldn't feel the arm at all, but the motor nerves, the nerves that command the arm to move, were left completely intact.
So, logically, the monkey should still be able to move the arm. It just wouldn't be able to feel it.
Exactly. But that isn't what happened. When the monkey woke up, it refused to use the deferented arm. It kept it tucked against its chest and navigated the world using only its 3 good limbs.
And the scientific community assumed this meant sensory feedback was strictly required for motor output.
But Taub hypothesized something completely different. He suspected the paralysis wasn't biological. He suspected it was psychological. He called it learned non-nous.
Learned not nous. How does that mechanism work?
Well, Taub theorized that immediately after the surgery, the monkey experiences a phenomenon called spinal shock. For a brief period, the motor system is genuinely overwhelmed and the monkey fails to move the arm.
It tries, but it can't.
Right. The monkey tries a few times, fails, and gets frustrated. Meanwhile, the monkey discovers it can easily get food and swing from branches using its 3 healthy limbs.
It's like encountering a ridiculously hard level in a video game. After failing 50 times, you just stop playing and eventually you forget the controls entirely.
That is a perfect analogy. The brain is an efficiency engine. It calculates the energy cost of struggling with the impaired arm versus the ease of using the good arm, and it makes a ruthless biological choice to simply stop trying.
So Taub proved this with a controversial but brilliant intervention. He took the monkey's healthy arm and completely immobilized it in a sling.
Yes. He constrained the good arm, leaving the monkey with no choice. If it wanted to eat, it had to attempt to use the defermented, paralyzed arm.
And the monkey moved it. Because the motor nerves were always intact, the monkey had just learned to stop sending the signal.
Exactly. And Taub realized this exact phenomenon of learned non-nous was happening in human stroke victims.
Because when a stroke damages the motor cortex, it leaves a core of dead tissue, right?
Right, but it also surrounds that core with a penumbra, an area of stunned, inflamed tissue that isn't dead, but isn't functioning properly either.
So a patient wakes up, tries to move their hand, and the signal can't get through the stunned tissue. They fail. They try the next day, fail again. And because humans are highly adaptable, they start doing everything with their good hand.
They learn to eat, dress, and write single-handedly. And this is where neuroplasticity actually works against the patient.
Oh, because of competitive plasticity.
Exactly. The brain maps in your motor cortex operate like highly contested real estate. If you stop using your right hand, the neural map dedicated to your right hand stops receiving electrical traffic.
And the brain hates wasted space.
It despises it. So the adjacent maps, say the map for your face or your shoulder, will physically grow and invade the silent territory of the hand.
The brain literally overwrites the software for the hand because it assumes you don't need it anymore. The paralysis is locked in biologically, not by the stroke, but by the lack of use. The brain map shrinks away.
Which is why Taub developed Constraint-Induced Movement Therapy, or CIMT. He took stroke victims who had been paralyzed for years, people who were 10 or 20 years post-stroke.
Long past that mythical 6-month window.
Way past it. He placed their healthy, fully functioning arm into a massive mitt for 90% of their waking hours.
He constrained the good limb to force the brain to confront the learned non-nous.
Then he put them through grueling, intensive physical therapy using only the paralyzed arm. They had to try to pick up blocks, trace shapes, and feed themselves.
That sounds agonizingly frustrating.
It was, because their brain maps for that arm had literally withered away. But that intense frustration is actually the biochemical trigger for neuroplasticity.
Oh, right. Because when the brain encounters a problem it cannot solve with its current architecture, it releases a flood of neurochemicals, including brain-derived neurotrophic factor, or BDNF.
Yes, BDNF is essentially miracle-grow for the brain. It triggers the consolidation of new synaptic connections. By forcing the repetitive use of the paralyzed limb, the patient's brains were forced to upregulate BDNF.
The surviving neurons in the motor cortex started rapidly sprouting new dendrites, physically building new neural pathways that routed around the dead stroke tissue.
The brain reclaimed the lost real estate, and the results were staggering. Patients who hadn't opened their hands in a decade regained full range of motion. They could write, they could lift glasses.
Taub proved unequivocally that physical recovery has no expiration date. The 6-month window was a myth generated by the brain's own efficiency protocol.
If you challenge the brain intensely enough and prevent it from relying on easy compensations, it has no choice but to rewire its own physical structure to meet the demand.
If intense forced exercise can rewire physical paralysis, can a similar approach fix structural deficits in cognition and intelligence? I mean, can you isolate a weak brain region responsible for intelligence and force it to grow?
Well, the neuroscience of learning disabilities has historically been just as fatalistic as stroke recovery. If a child struggled with spatial reasoning or logic, the educational system viewed it as an immutable genetic trait.
You were just built that way.
Right. But a woman named Barbara Arrowsmith-Young proved that cognitive deficits are just localized areas of neural underdevelopment.
Barbara's own brain was such a fascinating landscape of extremes. She had a brilliant auditory memory. If you read a book aloud to her, she could memorize it perfectly.
But she had devastating, highly specific structural gaps in her neuroanatomy. She suffered from severe deficits in spatial reasoning, reading, and logic.
Her subjective experience was incredibly disorienting, wasn't it?
Very. She couldn't understand cause and effect. She couldn't read an analog clock because the spatial relationship between the hour hand and the minute hand meant absolutely nothing to her.
So she just lived in a fragmented world where she couldn't connect concepts. And the experts of her era deemed her permanently impaired.
But she refused to accept this. She stumbled upon the early research on neuroplasticity, specifically the concept of targeted neural stimulation.
And she hypothesized that her spatial reasoning deficit wasn't a life sentence. It was just an underperforming neural network that lacked a robust density of synaptic connections.
Exactly. She realized she needed to treat her weak brain regions exactly the way Edward Taub treated a paralyzed arm.
She needed a brain, Jim.
She needed to put her spatial reasoning network through a rigorous, isolated gym routine. But here's the biological challenge. How do you isolate a specific cognitive network?
Right, because if I want to isolate my bicep, I do a preacher curl. But the brain is a massively interconnected web.
Exactly. If Barbara tries to solve a spatial puzzle, her brain will naturally try to use its strongest pathways, like her auditory memory, to compensate and find the answer, leaving the weak spatial network completely unchallenged.
It's like the monkey using his good arm.
Spot on. That is the genius of her intervention. She had to design exercises that completely overloaded her strong networks, rendering them useless while heavily taxing the specific weak network she wanted to target.
So to fix her inability to understand spatial relationships, she created the multi-handed clock exercise.
Yes. Instead of a normal clock, she designed computer programs featuring clocks with 3, 4, up to 10 different hands, and none of them function normally.
So one hand might represent days, another represents milliseconds, another represents years.
She would force herself to look at this immensely complex, abstract spatial problem and decipher the exact time. At first, it was agonizing mental labor.
Because she couldn't use her auditory memory to brute force the answer. The visual-spatial relationships were just too complex to memorize.
Right. She was cognitively constraining her healthy networks, forcing the electrical traffic to flow exclusively through her damaged spatial processing centers.
And that intense cognitive load, the sheer frustration of trying to hold those spatial variables in her working memory, triggered the exact same biochemical cascade we saw in the stroke victims.
Yes, she was bathing her spatial cortex in acetylcholine and BDNF, forcing the neurons to sprout massive new dendritic branches.
By doing this for hours every single day, she physically thickened the neural architecture of her spatial reasoning centers.
The synapses became denser, the processing speed increased. She literally eliminated her own learning disabilities.
The analog clock made perfect sense, cause and effect crystallized. She rewired the physical hardware of her intelligence.
And she proved the concept so thoroughly that she went on to found the Arrowsmith schools, putting thousands of children with severe learning disabilities through these targeted cognitive isolation exercises.
Children who were told they would never read or grasp mathematics are now thriving, purely because they built the necessary neural bridges through intense, focused effort.
It is a radical democratization of intelligence. We are not bound by the initial genetic lottery of our brain maps. We can consciously intervene and sculpt our own cognitive capacities.
Up to this point, neuroplasticity sounds like an absolute miracle cure. I mean, it cures balance loss, it cures blindness, it reverses paralysis, and it fixes learning disabilities. But there is a massive catch.
You are hitting on what Norman Doidge calls the plastic paradox.
The plastic paradox.
The critical thing to understand is that neuroplasticity is not inherently good. It is a strictly neutral biological mechanism. It does not have a moral compass.
It doesn't distinguish between a healthy behavior and a destructive one. It only responds to repetition.
It is a blind builder. Whatever blueprint you hand it, it will construct.
If you repeat a positive behavior, like practicing a piano chord, your brain strengthens that pathway. But if you repeat a negative behavior, a toxic thought pattern, a chronic worry, or an addictive behavior like smoking or gambling, your brain is actively strengthening the neural pathways associated with that destruction.
I think a good way to visualize this mechanism is to imagine sledding down a snowy hill.
Oh, I love this analogy.
The very first time you take a sled down fresh snow, the path is rough. You bump around, it's slow, and it requires effort to steer. That is a new neural pathway.
But if you take that exact same path down the hill 100 times, you carve a slick, incredibly deep groove into the ice.
Eventually, it takes zero effort to slide down that specific path. The sled flies down at lightning speed, and more importantly, it becomes almost impossible to steer your sled out of that route once you start moving.
That sledding groove is the perfect metaphor for a biological process called myelination, isn't it?
Yes. When a specific neural pathway is used repeatedly, specialized cells called oligodendrocytes wrap the axons in a fatty white substance called myelin.
Myelin acts like electrical insulation, and it drastically increases the speed at which action potentials travel down the nerve.
It turns a dirt road into a fiber optic cable. A heavily myelinated pathway can fire up to 100 times faster than an unmyelinated one.
Which is why bad habits and addictions feel completely automatic and effortless.
The destructive pathway has been so heavily reinforced, so deeply myelinated, that the moment a trigger is introduced, the brain defaults to the path of least resistance.
The signal shoots down the toxic pathway before your conscious prefrontal cortex even has time to apply the brakes. We literally wire ourselves to fail.
Which reveals why our intuitive strategy for breaking bad habits is biologically doomed.
Here's where it gets really interesting, because when we want to stop a bad habit, our instinct is to focus intensely on stopping it. We sit there and think, don't smoke, or don't bite your nails.
But from a neurological perspective, what happens when you intensely focus on the behavior you are trying to avoid?
You are actively firing electrical signals through that exact neural network.
Exactly. To suppress a thought, the brain first has to activate the representation of that thought. By obsessing over not smoking, you are keeping the smoking pathway illuminated.
You are pumping blood and electricity into the very circuit you want to destroy. Just trying to ignore it is biologically doomed to fail.
You cannot delete a neural pathway by fighting it.
So how do you dismantle a hyper-efficient, deeply myelinated toxic circuit?
If we connect this to the bigger picture, you have to utilize the opposite side of Hebbian theory. If neurons that fire together wire together, then neurons that fire apart wire apart.
Neurons that fire apart wire apart.
This is a process called long-term depression, or LTD. To break a habit, you must actively build a competing neural pathway. You must starve the old pathway of use so it can naturally weaken.
You don't try to fill in the deep sledding groove. You just force yourself to build a brand new groove on the other side of the hill, and eventually the old one fills with snow.
Right. When an old neural pathway goes completely unused, the brain's efficiency protocol kicks in. The brain realizes we are spending metabolic energy maintaining this massive insulated pathway, but no action potentials are flowing through it.
So, the brain deploys immune cells called microglia, which literally eat away the unused synaptic connections. The pathway naturally weakens and physically prunes away.
This concept of biologically starving a toxic pathway is the exact key to treating one of the most notoriously stubborn and agonizing mental health conditions, obsessive-compulsive disorder, or OCD.
The OCD brain.
For a long time, severe OCD was viewed strictly as a biological hardware malfunction, and the primary treatment was heavy medication.
But psychiatrist Jeffrey Schwartz deeply understood the neuroanatomy of OCD, and he hypothesized that he could use the principles of neuroplasticity to rewrite the hardware using only the software of conscious thought.
The neuroanatomy of an OCD loop is a brutal mechanism. It involves a specific loop in the brain getting stuck in a hyperactive state.
Right, it involves three parts of the brain. First, you have the orbital frontal cortex, which is your error detection center. It senses when something is wrong.
When it detects a problem, it signals the cingulate gyrus, which triggers a visceral feeling of dread and anxiety.
The cingulate gyrus then signals the caudate nucleus, which acts like an automatic transmission.
The caudate is supposed to allow you to shift gears, perform an action to fix the problem, and then clear the error message so you can move on.
In a healthy brain, you think, my hands are dirty. The error is detected, you feel a slight urge, you wash your hands, the caudate shifts gears, the error clears, and you walk away satisfied.
But in an OCD brain, the caudate nucleus is physically locked. It is a biological hiccup.
The error message fires, the anxiety spikes. The patient performs the compulsion washing their hands, but the caudate fails to shift gears.
The error message never clears, so the orbital frontal cortex fires again, harder this time. The patient washes their hands again.
The loop gets locked in a hyperactive, self-sustaining state. firing endlessly and sending false emergency signals.
But I know what you're thinking. If we are looking at a physical hyperactive brain circuit where the neurons are firing uncontrollably, how can a non-medical, purely psychological trick fix a biological hardware problem?
Exactly, that's my question. If the caudate nucleus is physically misfiring, thinking happy thoughts shouldn't be able to turn off the electricity.
Because the prefrontal cortex, the seat of conscious executive control, has direct inhibitory pathways down into the basal ganglia where the caudate nucleus lives.
Oh, wow.
Schwartz taught his patients that their focused attention was a physical force that could interrupt the automatic firing of the circuit. He developed a highly structured four-step cognitive therapy protocol: relabel, reattribute, refocus, and revalue.
Let's break those down. The first two steps, relabel and reattribute, require intense cognitive distancing, right?
Yes. When the overwhelming urge hits, the patient must consciously force themselves to observe the feeling objectively. They tell themselves, this is not a real danger, this is just an obsessive urge caused by a faulty brain circuit.
They are relabeling the feeling from a genuine threat to a biological glitch. They are creating a mental wedge between their consciousness and their neuroanatomy.
But cognitive distancing alone isn't enough to rewire the brain. The profound neurological shift happens in the third step: refocus.
The incredible power of a 15-minute rule.
This is where they actually starve the loop. Once the patient has relabeled the thought, they must immediately pivot their attention to a wholesome activity for at least 15 minutes.
They might go garden, play a complex video game, do a crossword puzzle, or build a model. The activity just must require focused, sustained attention.
This is the biological mechanism of long-term depression in action. The OCD circuit is screaming for completion. The neurons are demanding that the patient wash their hands to discharge the anxiety.
But by consciously refusing to perform the compulsion and forcing their visual and motor cortices to focus on a crossword puzzle, the patient is actively diverting electrical energy away from the OCD loop.
They are sending the action potentials into a new, healthy neural pathway. The OCD loop is denied the electrical reinforcement of the compulsive action.
By doing this repeatedly, day after day, the patient physically starves the obsessive circuit of energy.
And without that electrical traffic, the microglia sweep in. The synaptic connections in the OCD loop begin to weaken. The pathway physically degrades.
Brain scans of Schwartz's patients taken before and after the therapy showed massive, permanent changes in their neuroanatomy, didn't they?
The hyperactive metabolism in the orbital frontal cortex and the caudate nucleus had completely normalized. They had successfully thought their brain into a new physical shape, effectively breaking the loop.
It is a stunning testament to the fact that our conscious attention is the ultimate sculptor of our neurobiology, which forces us to look at the other end of the spectrum. We know how to rebuild damaged networks, bridge cognitive gaps, and break bad habits. But how do we protect the healthy brain from decaying as we age?
This brings up a universal anxiety. As we age, we fear losing cognitive sharpness and memory. We tend to view cognitive decline as a tragic, inevitable consequence of biological wear and tear.
You just assume the machine gets old and breaks down.
But the leading pioneer in neuroplasticity, Michael Merzenich, ran a series of experiments that proved this fear is largely misplaced. Merzenich discovered the biological reason for cognitive decline. It's not mostly time, it's disuse and a profound lack of novel stimulation.
The culprit is our own comfort zones.
Yes. To understand why, we have to look at a neurotransmitter called acetylcholine. When you are a child, the world is entirely novel. You are constantly bombarded with new sensory information.
Because everything is a high-stakes learning environment, the brain is constantly pumping out acetylcholine. And acetylcholine acts like a massive save button for the brain.
Exactly. It heightens neuroplasticity, allowing you to rapidly encode new memories and build dense neural networks. But as adults fall into routines, something dangerous happens.
We master our environments, we get a job we know how to do perfectly, we commute on the exact same route every day.
When everything is known, the brain shifts out of learning mode. It stops releasing acetylcholine because there is no novel information that needs to be urgently saved.
And without that steady wash of acetylcholine, the brain's plasticity machinery powers down. The neural networks that control processing speed and memory recall begin to physically atrophy from a lack of intense demand.
The cortical maps literally blur together, which is why older adults often struggle to quickly recall a name or process rapid speech.
So the standard advice telling retirees to do the Sunday crossword puzzle to keep their brain sharp is completely insufficient. If you have been doing crosswords for 20 years, your brain is already hyper-efficient at doing them. It requires zero novel adaptation.
Doing a crossword puzzle doesn't release acetylcholine. The antidote requires you to actively shock the system.
You have to step completely outside your realm of competency. You need highly demanding, novel activities.
You need to attempt to learn a new language from scratch. You need to pick up a violin if you've never played an instrument. You need to force your motor cortex to learn complex coordination, like ballroom dancing or juggling.
You have to subject yourself to the agonizing frustration of being a beginner again, because that intense mental fatigue and frustration is the literal sensation of your brain waking up, releasing acetylcholine, and forcing your neurons to sprout new dendrites.
What's fascinating here is that Merzenich proved an old brain can physically become fast and sharp again.
Through specialized training programs.
Yes, he developed rigorous, computer-based cognitive training programs designed to forcefully push the brain out of its comfort zone. In clinical trials, he demonstrated that this physically reverses the cortical blurring. Processing speed accelerates.
If our individual environments and routines shape our individual brains so drastically, what happens when we look at the environment of our entire species? What happens when we zoom out?
We enter the macro view cultural evolution and the plastic future. Culture isn't just art or ideas, it is a powerful environmental sculptor. Neuroplasticity shapes human culture and society, and our tools continuously rewire our mental architecture on a mass scale.
The most profound historical precedent for this is the invention of written language. Humanity literally repurposed visual cortex real estate to interpret abstract symbols.
Reading and writing are not innate biological functions. We didn't evolve a reading center. We hijacked a section of the visual cortex, an area originally evolved for tracking animal footprints, and we forcefully converted it into the visual word form area.
We rewired our visual processing centers to interpret abstract squiggles as complex language.
But if a physical book can permanently rewire the visual cortex of the human species, we have to address the elephant in the room: the digital age. Modern digital tools, constant connectivity, and social media.
These aren't just passing the time, they are physically reshaping your attention span and emotional regulation daily.
These digital environments are engineered around rapid variable reward schedules. The algorithms feed you a new, hyper-stimulating piece of information every 3 seconds.
Which triggers continuous microspikes of dopamine.
And dopamine reinforces learning. By constantly rewarding your brain for abandoning one piece of content to seek out the next, the digital environment is aggressively rewiring your prefrontal cortex.
It is systematically dismantling your biological capacity for sustained, deep attention. This is why, after an hour of scrolling, attempting to read a dense physical book feels physically agonizing.
Your brain revolts because you have actively downregulated the neural pathways required for quiet focus and heavily myelinated the pathways that expect constant, shallow novelty.
We must engage in conscious evolution.
Culture is a powerful environmental force. We must be intentional about our tech and media diets to ensure they expand our potential rather than diminish it.
Which brings us to the ultimate takeaway from this deep dive. The listener is the active architect of their own brain. It is never too late, and you are never too old or too broken to change.
Your mind is a living, dynamic landscape.
Embrace challenge, seek novelty, nurture brain health with deep sleep and physical movement, and replace destructive loops with deliberate positive actions. You have the power to starve the bad and deliberately feed the good.
If every single thought and experience leaves a physical imprint on your neural substrate, what is the exact layout of the blueprint you are drawing for your brain today? Are the tools in your pocket building the mind you want, or the mind someone else designed for you?